So just a reminder that you have things you can differentiate on your formula sheet, okay? And I'm going to get you to do a couple of different ones for me. So if you haven't got your formula sheet, I've got the page here for you. Page 6 in the formula sheet, just to save people digging around. So this first question was a really good one because it highlights how to differentiate any trig function squared. So a reminder that we write it like that before we differentiate it. So if I differentiate that, I get 2 lots of that, multiplied by the power, reduce the power by 1, and then I need to multiply by what you get when you differentiate the bracket. So that gives you 2 sine x cos x, which of course is sine 2x, and if it's 3 lots of that, it becomes 6 lots of that. That's good. This you could just look it up on the formula sheet. Look it up on the formula sheet. So can I get you just to quickly differentiate for me sec squared 2x using a similar approach? Can you differentiate sec squared 2x, which wasn't in the homework, using a similar approach? Okay? Yeah, I'm asking you to differentiate sec squared 2x as a further example of this. So you haven't got to write it as 1 over cos. You can just do it as a bracket using the formula sheet. So we get that. All right, so we can use the bracket approach, multiply by the power, reduce the power by 1, then multiply by what you get when you differentiate the bracket with pretty much any function. And for some things, the formula sheet makes it really easy. And the second part in that question was another example of a bracket where it was weird and wacky. So I multiply by the power, reduce the power by 1, and then multiply by what I get when I differentiate the bracket, which gives me 1 plus 1 over 2x times 2, because that's how you differentiate ln of 2x. 1 over 2x multiplied by what you get when you differentiate that, and that of course cancels down to 1 over x. And I left that, I didn't simplify that. I mean, I suppose you could have multiplied it out, but that was perfectly okay, unless it was asking for a greater level of simplification. Okay? So you can use the brackets in a number of brackets approach differentiation in a number of different scenarios. And you know, we had all the way down here tan squared x, again bracket. So write it like this, multiply by the power, reduce the power by 1, multiply by what you get when you differentiate the bracket, which is on the formula sheet, Simple, simple, simple. Okay? Yes, Joe?
Does this work two ways? Like,
right.
Circles?
So, do you mean integrating?
No. Like with the sine goes to cos.
Yes. Yeah.
And you said it was the same with tan.
No, so tan is just, yeah, so if you differentiate tan, you get sec squared. If you integrate sec squared, you get tan.
But not if you differentiate.
No, no. So if you differentiate sec squared, well, we've just done it, haven't we? So, right. So I want to pick up implicit differentiation where we got to, and the question that I was going to do was question 10, which I forget, that was on the list of things, and I don't know whether people actually got onto it. So we're on page 256 in the book, and question 10, which I don't think you did either. So just have a quick look. Did you get onto that one, Aidan? Right. And George, you obviously weren't here. So can I get to have a look at page 256, question 10? That's, for those not here, that's in the paper book. I have a feeling it's on page 255 in the actual book, in the online book, sorry. Had you done it, Matt?
Yeah.
Oh, okay. I have got something you haven't done. Oh, no, in the online version it is questions, page 256 as well. So George, you remember that you differentiate x terms just as normal, and y terms, we just write them as normal multiplied by dy by dx.
Yeah, and use algebra to get dy.
So go on, Joe, what do you get when you differentiate?
Cos x minus sine equals 0.
No, so that's an easy mistake to make, but you mustn't make that mistake. When you differentiate a y term, it's multiplied by dy by dx. Okay? X terms differentiate as normal, y terms differentiate them as if they were x's, but then multiply them by dy by dx. And then it's fairly simple to rearrange it. And that's not cot, is it? Because it's a different variable. It's cos x over sine y. But what's the good news, Aidan, when we're asked to find the coordinates of the stationary points?
The gradient zero.
Say again, sorry?
The gradient zero.
So we're asking when does that equal 0, and why does that suddenly make it really easy?
You can multiply by some.
Yeah, we're saying that the only way that can be 0 is when cos x equals 0. We can multiply by sine y, and 0 is your friend. So within the range of values that we are dealing with, cos between minus pi and plus pi looks like that. So does that mean, Matt, we are going to get a turning point when x is minus pi over 2 and a turning point when x is pi over 2? The fact I'm asking you maybe suggests it's not quite as straightforward as that. So what am I going to do to work out the y values?
Go back to the first equation.
So I'm going to go back to the first equation and say, right, okay, I've got a value of x now. I want to work out a value of y. So I'm going to go back to my first equation and see what happens when I make x that, and see what happens when I make x that. And yeah, the result is not as straightforward as it seems, okay? So go on, just do that bit for me if you didn't get that bit done. So having got my x values, there's definitely potentially turning points when x is equal to this and this, but what's the y value going to be? Well, we always go back to the original equation. A bit more complicated, isn't it? Because we've got an implicit equation rather than just a y equals equation. Anyone want to work out calculator? Are you with us, Joe?
Yeah, I'm ready. Did you say why it can't be 0?
Sorry?
Oh no, because you're times it, so it's fine.
What are we talking about?
That's fine.
Are you back with dy by dx?
Yeah.
Just multiply by sine y. So you just end up with cos x equals 0. Yes, so we find that when x is minus pi over 2, we go back to our original equation, the sine of minus pi over 2 is minus 1. So we end up with cos y is 1.5. No solutions. So even though x, with the turning point could potentially have been here, it can't be here because there's no valid solutions. So instead, let's try pi over 2 into the same original equation. Sine of pi over 2 is plus 1.
So what's going on when you get a solution that's not a solution?
I must admit, I was doing this last night, I was trying to get my head around it.
Is it like a point where the line isn't that it would be that if the line was there?
Yeah. Yes, implicit functions do have this added complication, which you've got to be valid for both x and y, because dy by dx involves both x and y. So I guess yes, I haven't got an easy answer for that one. What we do get is two turning points where x is pi over 2, though, don't we? So when I do shift cos of minus a half, I know I'm going to get two answers, and one positive and one negative. Sorry, Joe, what were you going to say?
I think it's just an x value that works for the equation, and there's only a turning point that looks at the y.
Yeah, well, yes, that's absolutely the case, but the gradient is 0 at that value of x. That was what Matt's saying. So how come but it has to be valid for x and y. That's the thing. So we get 2 turning points, but both of them come from the pi over 2 solution, nothing from the minus pi over 2 solution. So we do have to be careful with implicit equations that we don't get sort of caught out by that. And I found 2 other questions. I couldn't find anything in the textbook on this, but I found 2 other questions which have that extra little bit of difficulty involved. So I hope these are visible on the camera as well. So the first part of the first one is pretty straightforward. So you're going to differentiate that function. You've got a product in there. And you're going to work out the tangent at this point by working out the gradient at that point, and you know the point. It's the second part, which is non-straightforward. So have a go at the first bit. This is not a turning point question, but it requires a little bit of going back to the original function action. So George, x terms just become differentiated as normal, y terms differentiate as normal and then multiply by dy by dx. Constants disappear. That's a product for x times y, so we've got to do that with the windows.
So yeah, just 4 and then dy.
One dy by dx, which I'm just going to write as dy by dx, and then remember the product rule is those 2 added to those 2. I think it's quite good to try and do that next step in one go. So remember what we're doing is we're moving everything without a dy by dx onto the left-hand side, onto the right-hand side, factorising the remaining side, and then dividing by the bracket. So that would give me and I'm going to divide by -2 just for kicks.
What if there was y cubed? Would it just be
Y cubed would be
Yeah.
2y squared dy by dx.
no the 3y? If it's 3y cubed, does it just still dy by dx?
Yes. Yeah.
It doesn't change.
Just differentiate as normal, and then because remember what we're doing is we're multiplying it as if the y is in a bracket. So we're just doing the bracket thing, multiply by the power, reduce the power by 1, and then multiply what you get when you differentiate the bracket. And if that's a y, what you get is dy by dx. Gradient -4. So it's the next bit that I really want to talk about, so I apologise if I've rushed you a little bit with part A, but I'm fairly relaxed that you'll be able to do part A in your own time had I not given you that time. So part B says, given that the tangent to the curve at the point Q, different point, is parallel to the tangent of P, find the coordinates of Q. So what we're saying is there's another place where dy by dx equals -4. Okay? So we've solved part A, we've got our answer. They're saying there's another place. We know about the point 4, 2, but there's another place where this gradient equals -4. Find that place. And the problem I have is I can't do that from dy by dx, because dy by dx is an equation with x and y. So all I can do is get an equation that's relating x and y. Can I get you to do that much for me? I hate fractions, so I'm going to multiply both sides by the denominator. Can I get you to simplify that such that you just get an equation that says either x is something to do with y or y is something to do with x? Okay? So just simplify that so that we're not going to get the x value, we're not going to get the y value. All we can get is a relationship between y and x. So I'm hoping you've got that at this point x is equal to 2y, which, yeah, we saw already. But we couldn't assume that that was the relationship because it might have been, you know, at x is equal to y plus 2. But that still isn't going to tell us the coordinates. You know, is it going to be 8, 4 or 6, 3?
-4. Okay.
So Aidan, how can I work out what the coordinate actually is? I know that x is equal to 2y.
Substitute it into the equation this time.
So we go right back to our first equation. That's right. Right back to that first equation. I could replace y with half of x. I'd be crazy. I'm going to replace x with 2y, get a quadratic in y, and solve that to get my y value. And then I've got this equation down here telling me what the x value is. So going back to the original equation, common theme with question 10 from the textbook, with this one, and a common theme in the next one. So see if you can get somewhere with that. Then have a go at this one, and then 3 questions from the book. Okay? Have you got an answer to?
I haven't done that.
Okay. So because we've got x and y in dy by dx, it doesn't always give us the full answer. We often have to go back to the original equation to fill in the piece of the puzzle, or the pieces of the puzzle that we're missing. So we're not differentiating, we're just substituting. We're replacing x with 2y. No. Really easy quadrant. Mind you. So always remember you can use your calculator at that point, but you know, it was a lot more straightforward than that, wasn't it? I was a bit worried, I was thinking, hang on a minute, I'm looking for a point and I've got two y values and x is equal to 2y. So I was a bit worried, but of course we already know about that one. That point we've already been told, that's p, so the value we're after, the coordinate we're after, q, must be -4, -2. Okay, have a go at this one. Here we're going to differentiate parallel to the x-axis. George, what is the gradient of a line when it is parallel to the x-axis?
0.
0. So it's a funny way of saying turning point. And we're definitely talking plural. But it's another one where you're going to have to go back to the beginning and then 3 questions from the mixed exercise to draw this to a close. And they're real doozies, so they're worth getting your teeth into. Any questions about that first one?
How many marks?
Good question. No idea. They
10.
came from. Where did I get them from?
9.
Actually, I'll show you where I got them from.
8?
3 then 4, I think.
No, you're crazy.
Well, I can show you. I'll show you where I got them from.
Obvious 5, wasn't it?
I would have a bit of
So, one note, independent revision, differentiation, and I'm trying to be less directive, aren't I, this time, but I did put that basic practice on, but then I've linked here to the Physics and Maths tutor page on Year 2 differentiation, and this is, I strongly recommend this because you've got these questions here are on everything that we need to do, and they're really, really good. So I think and then down here, you've got even better. These come from old syllabus worksheets, and I have a feeling that I got them, the implicit ones from here. We'll just have a look. Yes, and no marks. Sorry, it doesn't but my point is that if you want practice, you've got 2 places. You've got here, which are sort of exam type questions, and then here you've got worksheet type questions, and there is more practice there. And the ones at the end are the ones you probably want to go for now, because they're the harder sort of longer ones, whereas these ones up here tend to be a bit more basic. So that's all linked to from OneNote differentiation page under independent revision and that link there.
How is that less direct though? Is it because you put the link instead of the file?
No, I think before I've given you a very specific list of questions to work through. Now I'm just saying it's all over there.
Okay.
Choose what you need to do. I mean, yeah, that's a very long list. I'm not expecting anyone to work through all of those. Got another product mixed in this one, so I've got to use the windows to differentiate x squared y. I mean, it's not complicated, but it's just need to spot it.
Is there a shorthand for dy to dx?
Well, no, only f dash of x as an alternative, so no, sorry.
What about I don't know.
I've seen people use like y and then just like a dash, so not like functions.
Is it really that much effort?
Oh, it looks a bit cleaner.
There we go. I don't know. If you maybe that's something you'd learn if you went to university, George.
If you were just y dash, wouldn't that just be dy? Because it's not always dy over dx, is it?
Yeah, no. So no, f dash of x is the notation we use, not y dash.
If you just differentiate, like if you had an x equation or whatever, and you just put d over dx, that's what they use on the homework. Like if you had an x, especially with just x, and you want to differentiate, you put d over dx.
Well, no. What they sometimes write is what's d of x squared over dx. That's 2x. That's some.
No.
You can separate that into d over dx of x squared.
Yes. Yeah. Anyway, return to this question. Because I've got x and y in my numerator, I can't get a nice satisfactory value for x or y. I end up with this relationship again. So I know that where the gradient is 0, this is true, but that doesn't tell me anything about it. So what I need to do, surprise, surprise, back to the original function. Okay?
Why did you times y minus 1?
Why did I times y minus 1? I don't know, did that trouble
You
you?
just did it the wrong way. You did it the other ways.
Right, okay, but we should end up with the same relationship at the end. Yeah, right. You moved everything over there. Yeah, I guess I would agree that yours was probably more sensible this time. So we are looking for these points, and this time, unlike number 10 we did, the first one we did, we actually got the x values at the turning point. We've got no such information at the moment. All we know is that at these points where the gradient is 0, the x value is minus 1 over the y value. So I'm going to substitute that into my equation. I'm actually going to use xy is minus 1 as well, because that will help me when I get to this one. Just, it's not earth-shatteringly different, but it's... Actually, I said plural earlier, didn't I? The coordinates of the point, that's definitely singular, which is relief, because I'm only going to find one point. So it looks horrible, I multiply by y, looks nice. And the nice thing about cube rooting, of course, is there is only one answer. You haven't got to worry about plus or minus. So I've got my y value at this point. X is minus 1 over y. So minus 1 over minus 1 is plus 1.
I didn't get the same issue. You get minus. No.
Sorry, where did I lose you?
You're good.
Sure? Yeah, when I did the substitution, I rewrote x squared y as x times xy, because I had an xy statement, and I mean, it just speeded that bit up. Could have done it. Without
What did
doing
you?
it. Okay, so 2, 6, 8, 30, 31 and 33. I'm going to stop the video at this point.